This is the very first test distribution. It's going to be based on the Z distribution, and you will be able to figure out why it's the Z distribution was going to be based on normal distribution as well. So it's really normal distribution basically has a requirement where we use the Z value in order to determine whether to reject the null hypothesis or uh, fail to reject it. I like to use the term fail to reject it instead of accept because accept is not really a 100% accurate term, but just to make it easy, you could use it. But in reality, when you're trying to write something in a kind of published material or something you need to share, you have to really look at that exact wording. Anyway, just to make it simple, let me give you this problem. So I'm going to verbally state it, and I want you to listen very carefully to it. So let's assume that uh, a college professor wanted to verify that his group of students in the university that he teaches have an average IQ that is larger than what is normal. So for me to really figure out this, I have to uh, come up with the data that is already been tested based on the population in general, maybe everybody in the United States. And in reality, really, the standard deviation for the uh, IQ test is 15, and the mean is usually is 100. So this is classic values. And so since the mean of the population is 100, so the hypothesis test is going to agree with it, agree with the fact that, as we'll see here, mu, I need to really get the mu here, is going to be equal to that 100, of course. And the alternative hypothesis, since I'm saying this person or the professor need to look if, or he claims rather, that the mu for his group of students is going to be bigger than the 100. In order for me to verify if he is really going to accept his claim or to not accept his claim, I need to tell him, okay, you said to me that you don't agree. How are we going to verify this? I need to come up with a sample. The sample need to be greater than or equal to 30. Make it big enough. And since we have the standard deviation for the IQ from the population, we are in good shape. We will be actually using that Z distribution as a result of this. But you have to give me another critical piece based on a sample, the number of that sample, and also the number in the sample, and also the standard deviation that you uh, uh, calculated. But since we already know the standard deviation for the population, I don't need a sample standard deviation. And in this case, I will ask him just to give me the number for the sample. And he told me it is actually it's going to be, let's say, 65. So this is actually satisfy my need that's greater than or equal to the standard deviation for the population, also known. I'm about to go ahead and continue with my hypothesis testing. Before we even attempt to do anything with this, I'll say how comfortable you are with the result based on a confidence level. Would it make you happy if I get 90% confidence level, or 95% confidence level, or 99% or 98? This guy is really kind of determined that his students, his IQ is very high, and he said to me, "All right, since he did find that the X bar, the X bar to be 131, said, oh, you could even test it at 99%. I don't care." So the alpha is going to be here at the alpha is going to be at 0.01 because he said he is confident 99%. So I thank you for giving me the X, which I almost forgot to ask you about it, which is the, what do you call it, the mean for the sample of the 65 students. He asked them for their IQs, or he tested them for IQ. Who knows how did he get it at this moment, but at least he's honest enough to assure us that he got that 131 from a kind of valid test. So now I have everything I need to calculate the z-score. But before we do the z-score, we need to go ahead. Let me go ahead and put this number 2. This is number 1. And I'm going to go ahead and do everything here as centered. So I will know this step 2 is step 3, 2, this step 3. I need to get that critical region, and I'm going to be actually using now the value for the critical region, where I'm going to be using Minitab, and I'm going to bring it here to the area where you could see it. And then I'll take it back to where it belongs, to the right. And I have now an alpha of 0.01. And I have to test to find out the critical region to where is actually Z is going to be able to start that rejection region. And remember, the alternative hypothesis, alternative hypothesis is to be greater than. That's what he is assuring us, that is greater than. So I'm going to go ahead and go to the graph, go to the probability distribution, go to this view probability. I'm going to do this. Also, I'm going to leave it, which is the default one is normal. Of course, later we're going to change this to t, to change it to also to the chi-square. So you have to really very careful to which one of those distribution we are using. At this time, we're going to use the normal, which is the default one anyway. So make sure that you understand this. Since I'm only going to get the critical value, which I could easily do that through any software, through 100 of online sites have this, the tables in the back of your book. But I'm going to stick with Minitab to help me with both things. Now for getting the critical value for Z based on one tail, because I'm saying here greater than, and also to do the test hypothesis with the calculation for me as well. And this way I'll be able to go one step at a time. So the first step is to go ahead and find the critical value for the region, for the rejection region. So I'm going to go ahead and go to the shaded area, leave it as the probability. The probability has to be changed to 0.01. Remember, he is very confident. And now we're going to say, okay, now he's saying greater, right tail, so it's greater. And I'm going to click on here. And you notice Z is very large. It's 2.326, which means, or even, I mean, a very large, even above 99.4%. You know, so fine. We'll go ahead and do. This is my value that I need to keep in mind. It's 2.326 or 2.33. That's what it would be. I'm going to go ahead and put it here. 2.33, and which is great, and that alpha. Now I'm going to calculate my z calculated. I'm going to put the little c here to indicate that I'm calculating my z that I need to compare to this one here in order to reject or not to reject the null hypothesis. So z is going to be, I'm going to actually do it. You don't have to use Excel. Nobody should be using anything that is not comfortable with for calculation. You could use your fingers, you could use your calculators, you could do whatever you want. I'm using Excel, as you notice, not for its full potential, which is huge, I mean, fantastic software, just as a calculator, so for the convenient. And I'm going to go ahead and fill this one here, you know, by satisfying all the requirements to see what is the calculated Z. So I'm going to go ahead and say, okay, he told me that the average or the means for the sample is 131, which is going to be minus the mu. As you notice, the mu, I'm going to waste time really pulling those special characters. So mu is going to be that mean, which is 100. That is going to divide it. Remember here, we have to take the standard deviation, which is 15, divided by the square root, which is a function in Excel, square root of the n, which is the 65. So this is actually the 15 divided by the square root of 65. This is cover for the standard error with the sample versus the population. I'm going to hit the enter to come up. Okay, here is that calculated Z. Let me go ahead and see here if I missed something. All right, I probably need to do some rule of order, you know. That's basically, it's a very critical, fact that I have to not the division by the 15, then the result is going to be divided by the square roots. No, this is going to be the denominator. So if you don't know, the use of Excel, Excel is very sensitive to the rule of order. So I got Z to be 16.622. Whoa, this is very huge value comparing to what I have. This is actually going toward infinity. So is it basically, I need to have anything bigger than 2.326 or 2.33. I got 16 point something. So it definitely falls in the rejection area here. As a result, you will see that we should strongly reject the null hypothesis that the mean is equal to 100 for that sample that this professor. So he's telling the truth after all. That's what I want to see to actually get that clear. So we could say here we reject the null hypothesis that the mean of the students, his students, of course, because that comes from his claim, is the mean of the students' IQs, is 100. That's basically. So I want you to be able to do all this manually. Remember, this is basically is a very important things to do through the Minitab or the book, but this is extremely important to do that by hand. You could write that down. You could down a piece of paper, then use your calculator. Then based on the value of Z, and sorry here, I'm going to go ahead and do here because I don't want to mess that up. Okay, and now we're going to be able to finish this video in a heartbeat because I'm about to go ahead and show you how we could do the same thing, which you will be responsible to do that as well. Show you how to do the whole thing through Minitab based on the giving data. So you have to do it by hand or manually using a calculator. Then also you're going to do it through the stat with the basis statistics. And we're going to go for a one sample Z score. And since I'm really not giving you all the items, I'm sorry, the values for the IQ of the sample, I'm summarizing everything as the sample mean, which is 131. So this is what we need to make sure. This is basically here on the top of this, where I'm clicking here to see one sample Z for the mean. And because by accident you might be clicking on something that is not representative of what you're trying to calculate. To quickly make sure that what we calculated by hand, which is the Z-score a little bit over 16 point something, and I need you also to get the p-value, which is another more important way of actually determine whether we need to reject or accept the null hypothesis. So let's go ahead and do this. A sample size is 65. And the sample mean was 131, and the known standard deviation is the 15. Then we're going to check on this. We need to really practice with this. The hypothesized mean is the one that goes along with the hypothesis test. So it's going to be 100. Make sure that whatever you made it equal to goes all the hypothesis null hypothesis, I'm sorry, the null hypothesis, with which is the HO, the little o, is going to be the value that is going to bring us the hypothesis mean. Click options. This person said he needs it to be at 99 confidence. See, this is basically 99 is what is 1 minus alpha. And remember, we decided to have a mean of greater than the hypothesis test. Okay, this is what it is. And I'm going to say okay. and we're ready to go ahead and run it. We should be able to get, if not 100% exactly to the value of z, but it should be, of course, extremely close to it. Here we go. That's basically what we ended up with. This is the value of z. Let me go ahead and make sure that you can see this. More importantly, that we can actually depend on using this extremely important value, which you should be able to mention something like this in a test or in a study, that the value of p, which is the b value for this test, must be less than the value of alpha, which is 0.01. If that is the case, we do the same exact things by rejecting the null hypothesis, because the z value here is much greater than the positive side of the rejection area. Remember, if we have another test with less than, then z is going to be a negative, and it's going to be must be also a smaller value, negative smaller value than the critical region, which is going to be also a negative. I could run this very quickly with another example. Not to worry about it. It's not going to take more than 1 minute. But in order to do this, first of all, we have two values to depend on the rejection. The z is much bigger than 2.33, and the p-value is much less than 0.01, which is almost zero. That's why it's so small. And we could conclude that we should reject the null hypothesis. Just to give you another example here, using the same stat in order to show you the basic statistics. I'm going to actually go to the graphs. Let's assume this person said to me the same exact things at 2.33. You know, that's the same exact data. But in this case, no, actually, let's change it a little bit so we can see it with better understanding. Let's say there's a different story than what we have. There is another professor who did actually, not feeling very good about the IQ of a group of students. Then he found out that the sampled mean for the IQ were, let's say, 89. Okay, so in order to do this, we have to figure out first what would be the z-score at in this case at 99% for 89. The n is going to be 89. So I could run this very quickly here, and I could show you the z value. It's going to be negative, all right. But the calculated z versus the table z, as I call it. Here we go. Let's go ahead and see the table z, which is at the mean 0, what points 1, and the shaded area is going to be, in this case, less than, because it's going to be less than, knowing that we are going to change the claim. He found out the average sample, or the mean for the sample is 89, and he said, yeah, there's 65 students I just tested. It's going actually having a lower, less than the typical mean for the population. So in this case, it will see the critical region for this new approach, which is less than. It's going to be, look here, minus 2.36. Okay, so any calculated z is going to be minus, less than minus 2.36 or minus 2.33. So if I do this in the study, basic statistics, sorry, and we're going to go to, again, basic statistics. We're going to do the sample for one sample for z. Now remember, the mean change from 130 for those people with a high IQ to another group with that sample mean of 89. You notice that 89 minus 100 is going to be negative. So the calculated value will be negative. The same known standard deviation, the same exact hypothesized mean. I'm going to go to the option. I need to leave that confidence level at 99. I'm going to change the hypothesis mean to less than, the mean is less than the hypothesis mean. And I'm going to go ahead and click. We're going to be getting some sort of a value of z in negative, but we don't know if it's going to be less than minus 2.33, even though I know how, but it's going to be approximately what, but Let's the software help us with that. And notice here we got minus 5.91. So based on that standard, based on this sample means, also the standard deviation and the means at minus 0.91, this is really falls in the critical region. And maybe, not maybe, for sure, we can reject the null hypothesis that this group of people is going to be, their IQ is equal to 100. However, it is really less than based on the study because we reject the null hypothesis in a way that we actually are happy with uh, the rejection of the null hypothesis. We do not want the null hypothesis because the z-value is minus 5.91 does fall within that critical region. Another way of looking at it is to see that the p-value is almost zero. This is again less than. That's why it's much better to do the p-value because you're not going to get the confusion of minus z and plus value for z. P-value always going to be compared to alpha, and as a result. But for introductory class and statistics, we need to know all these details. So anyway, this is also going to be rejected. Let's take another example. I know I'm going to take more time, but just one more minute. If I do the same stat for basic statistics, but now this person said he did actually do the average sample mean or sample average, and he found it to be 101, which is very close to 100, which is the sample, the population mean of 100. So if we run this, now we're going to change the sample mean to 100, and the same exact things are the 100, the sample mean is 100, and the high, actually he found it 101, sorry, 101, still it's 100, and we're going to go ahead and say, okay, option is still the same, and this is, of course, changed because 101 is greater, and that's what he's claiming, that he has a really strong evidence that these people have a higher IQ than the normals, and he found out the sample mean is 101, and whether we need to reject or accept the null hypothesis. So I'm going to go ahead and show you, in this case, the z-score is going to be 0.54. So the z-score based on the other one, which we have done, is 2.3, but it's in the positive. So when we say here, let me show it to you very quickly, the graph here. We talk about the probability distribution for new probability. The norm, the standard area here is going to be greater than, still the same probability. It's going to give me 2.33, 2.33. So if you take a look here, 2.33, the z-score 0.54 is way to the left of it. So it's not even touching the rejection region, and the p-value way bigger than 0.01. So we have to really accept the null hypothesis or fail to reject the null hypothesis because obviously that person does not have a group of students with an IQ that is much higher than or greater than the mean for the population. Thank you so much for watching this. I'm sorry this is a long video. I promise to make the other one a lot shorter, but that requires some kind of interface with the the Minitab. That's why it took longer.